It's wild to think that the ocean covers 71% of our planet, yet our bodies are just fundamentally, stubbornly built for the land. Welcome to this explainer. Today, we're taking a deep dive into humanity's incredibly complex relationship with the sea. It is a relationship packed with profound contradictions. We're totally drawn to the water, it fascinates us endlessly, but biologically speaking, we just don't belong there. We're going to explore how we've romanticized the ocean by trying to link our evolutionary history directly to the water, look at the harsh and sometimes deadly biological realities that keep us from returning to it, and uncover the incredible workarounds we've developed to study and protect this environment safely from the surface. We've got a lot of fascinating ground and water to cover, so let's jump right in. Here is our roadmap for today. First, did we evolve from water? Second, the aquatic ape controversy. Third, the dangers of deep diving. Fourth, understanding oxygen toxicity. And finally, educating the next generation. Section 1. Did we evolve from water? Exploring the origins of a persistent evolutionary myth. For the longest time, the classic story of our ancestors was heavily focused on the savanna hypothesis. You know the one? We came down from the trees, became mighty hunters, and evolved strictly on the dry, dusty plains. But for decades, a wildly different alternative stubbornly persisted in the public imagination: the aquatic ape hypothesis. It kicked off back in 1942, when a German pathologist named Max Westenhofer speculated that certain human traits came from an aquatic past. The idea really caught fire in 1960 when marine biologist Alistair Hardy presented a similar concept to the British Sub-Aqua Club. And here's a crazy piece of history for you. Hardy actually sat on this idea for 30 years purely because he was terrified his academic colleagues would mock him. He only spoke up when he felt established enough to take the hit. Later on, in 1972, screenwriter Elaine Morgan heavily championed the concept in her international bestseller, Descent of Woman, painting this super vivid picture of our ancestors waiting on the seashore instead of hunting on the plains. Proponents of this theory basically argued that our unique human features, things like our lack of body hair, our layer of subcutaneous fat, and even our ability to walk upright, were all adaptations for a semi-aquatic life. They figured standing on two legs made it way easier to wade into deeper water. But anthropologist John Langdon correctly classified this as an umbrella hypothesis. Think of an umbrella hypothesis as this really tempting cognitive shortcut. It tries to explain many separate, incredibly complex evolutionary developments using just one single magic bullet, in this case, living near the water. It's a fun way to look at history for sure, but biological evolution is rarely, if ever, that neat and simple. Section 2. The aquatic ape controversy. Why the scientific community overwhelmingly rejects the theory. Now, while the general public absolutely loved the idea of swimming ancestors, it even picked up celebrity endorsements. The mainstream academic community was brutally dismissive. Anthropologists overwhelmingly ignored it or just flat out rejected it. Listen to this quote from Henry G., a highly respected paleontologist and an editor at the prestigious journal Nature. He argued that the hypothesis has equivalent merit to creationism and should be similarly dismissed. Wow. Other physical anthropologists bluntly referred to it as crank anthropology, basically tossing it into the exact same pseudoscientific bucket as hunting for Bigfoot. The main critique was that the hypothesis is a textbook case of cherry-picking evidence to fit a romantic conclusion while totally ignoring mountains of opposing data. When you actually hold these claims up to the harsh light of real science, the illusion just shatters. The aquatic ape theory insists that our unique hairlessness and body fat prove we were meant for the water. But the actual scientific consensus, championed by anthropologists like John Hawkes, points out a massive, glaring flaw. The traits this hypothesis bundles together actually evolved millions of years apart. Plus, these physical features are perfectly normal for land-dwelling primates. We have them for very well-understood thermodynamic reasons. For example, our ancestors lost body hair so they could sweat and efficiently cool down while running on the hot land, definitely not to become hydrodynamically streamlined in the water like a dolphin. And above all else, the fossil record simply doesn't show a single trace of an aquatic ancestor. So, if we aren't built for the water, and the scientific consensus is crystal clear that we didn't evolve for it, we have to ask a pretty practical question. What actually happens to our biology when we force our way down into the deep ocean? Section 3. The dangers of deep diving. The physiological realities of the underwater world. Here is a stark irony about deep-sea diving for you. Oxygen is literally the key to all life on Earth, right? But in the highly pressurized underwater environment, the very gas keeping you alive becomes your absolute worst enemy. To understand this biological danger, we need to talk about reactive oxygen species, or ROS. As a diver descends, the crushing pressure of the water increases the partial pressure of the oxygen they're breathing. This intense pressure essentially forces oxygen molecules to collide, turning them into highly reactive ROS molecules. Think of these molecules as rogue bumper cars just tearing through your bloodstream, and what they do is truly frightening. They bind with nitric oxide molecules, which suppresses your sympathetic nervous system controls. This triggers what's known as an adrenergic storm. Simply put, your body's fight-or-flight response totally short-circuits and goes into a fatal overdrive underwater, leading to massively spiked heart rates, severe cellular damage, and ultimately seizures. Section 4. Understanding oxygen toxicity, when the gas that gives us life becomes deadly. Basically, any time you breathe a gas with an oxygen content higher than 21% under pressure, you are at risk. But there are actually two distinct ticking clocks when you dive, and it depends heavily on how long you stay down and how deep you go. First, you've got pulmonary oxygen toxicity, which scientists actually first noticed way back in 1899. This happens over very long, sustained exposures and results in severe lung inflammation. It's primarily a risk for commercial saturation divers, the folks whose jobs require them to live in pressurized underwater habitats for days or even weeks at a time. On the flip side, you have central nervous system, or CNS toxicity. This one hits the brain incredibly fast and hard at high pressures over shorter periods, making it the primary, deadly concern for recreational and technical scuba divers who are just out for an afternoon exploration. To prevent a catastrophic CNS seizure underwater, recreational divers have to rely on strict scientific math. They adhere to a maximum oxygen partial pressure limit of 1.4 atmospheres absolute, or ATA. To give you a little real-world context, that's roughly equivalent to diving about 130 feet deep while breathing regular compressed air. Technical divers, when they're just hanging on a decompression line and their bodies are at complete rest, might cautiously push that to 1.6 ATA. Sticking strictly to these mathematical limits and managing other risk variables like extreme physical exertion or retaining too much carbon dioxide is essentially building an invisible shield against the creation of those rogue, dangerous ROS molecules we talked about a minute ago. Now, if a diver ignores that math and pushes past the safe limit, they face the terrifying escalation of CNS oxygen toxicity. The medical field uses the acronym CONVENTED to remember the symptoms. And this isn't some slow, gentle onset. It starts subtly, maybe sudden tunnel vision, a ringing in your ears, a bout of nausea, or uncontrollable twitching in your facial muscles. But without warning, those symptoms can violently escalate straight into full convulsions. And here's what's truly scary. These seizures can strike without any of those warning signs at all, out of nowhere. It's often not the seizure itself that's fatal, but rather the massive likelihood of drowning or suffering a catastrophic lung expansion injury if a panicked, uncontrolled ascent to the surface is attempted while the airway is blocked. This leaves us with a profound paradox. The deep ocean is actively, physically hostile to human biology. So how exactly do we satisfy our relentless need to explore it without risking our lives? How do we understand this vast underwater world if we can't easily live in it? Section 5. Educating the next generation. Advancing ocean literacy and stewardship from the surface. Since we don't have gills and can't actually be aquatic apes, we rely on world-class institutions as our ultimate workaround. We've basically had to become aquatic scholars. We study the ocean and advance marine stewardship from the safety of the surface, using incredible resources like the Smithsonian Ocean Portal. The National Museum of Natural History houses the world's largest marine collection, representing research efforts that stretch back a staggering 160 years. The Ocean Portal brings the sheer scale of all that exploration right to our fingertips. Its explicit purpose is to increase public knowledge about marine science and inspire millions of online visitors to become caring ocean stewards. This entire mission is supported by the museum's three-pillared ocean initiative. You've got the massive Sand Ocean Hall exhibition, the Sand Chair for Marine Science, which leads the ongoing physical research, and the Digital Ocean Portal. But look, it's not just about having a big, beautiful building or a slick website. It's about impact. This initiative takes highly complex, incredibly dangerous deep-sea science and translates it seamlessly, bridging the gap between elite deep-sea marine biologists and the general public. It's perfectly designed so that anyone, from a young adult to a kid sitting on their laptop, can engage with the deep ocean safely and meaningfully. And they actually take that mission a step further by bringing the ocean directly into the classroom. The Smithsonian created the Ocean Planet exhibition and adapted its complex themes into interdisciplinary lesson plans for middle and high schoolers. They use lessons like Sea Secrets, which explores ocean geography, and Pollution Solution, which dives into the devastating effects of modern environmental crises. This isn't just about memorizing dry facts. It's about turning passive students into active defenders of an ecosystem they might never even physically visit. By doing this, they ensure that the critical importance of marine conservation reaches students everywhere, transforming raw scientific data into actionable, lifelong learning. As we wrap up this explainer, I want to leave you with a final thought to really ponder. We've seen today that despite our historical myths and those highly romanticized ideas of an aquatic past, the ocean is an environment that fundamentally rejects our human biology. We are land creatures through and through. Yet, the ocean remains the absolute lifeblood of our planet. So the question now is this: even though we can never truly call the deep ocean our home, will we step up and choose to protect it anyway? Thank you so much for joining me on this deep dive, and keep exploring.